Welcome back to my YouTube channel. My name is Muhammad Ubaid and this is another video of basics of structural analysis series. In this video we are going to solve another interesting problem by using conjugate beam method. So this is a prop cantilever beam and this beam is having an internal hinge at C, and this beam is also subjected to a point load of 25 kN at B and a concentrated moment of 48 kN meter at D. We will going to find out the slope and deflection at the internal hinge C by using conjugate beam method. We have solved this problem in our previous videos of moment area method series, and I have taken the same problem so that you can compare the problem solving procedure of both the methods, and you can also compare the results which we have got from moment area method and which we will got by using conjugate beam method for the same problem. Okay, if you are new to our channel, please subscribe to our channel. If you like this video, please share this video. If you have any confusion regarding any point, please comment down in the comment box. I will try to answer all your comment as soon as possible. So without any further delay, let's get started with the solution of this problem. So this is our problem, and as we are going to solve this problem by using conjugate beam method, so we have to convert this real beam into conjugate beam. First of all, we will convert the support condition of the real beam to the conjugate support conditions. Okay, so let us draw the beam first here. This is our A, this is B, this is C. Okay, this is C, and here we have our D. Now this fixed support which is at A will be replaced by a free end in conjugate beam, and this internal hinge at C will be replaced by a pinned support at C, and this roller support at D will remain same in the conjugate beam. Okay, this will not be replaced, this will remain same. If you want to understand how we change these support conditions from real to conjugate beam, you can watch the first video of this series. You will find the link in the description box. Okay, now we have converted the support condition from the real beam to conjugate beam. Now we have to convert the loading. Okay, so as we have learned in the first video, the loading for the conjugate beam will be M by EI diagram. Okay, so first of all we have to draw the bending moment diagram of this real beam, then we will convert the bending moment diagram into M by EI diagram. That M by EI diagram will be applied as the loading on this conjugate beam. So to find out the bending moment diagram of this real beam, we have to find out the support conditions, support reactions. Okay, so let us assume that the reaction at A is RA and the support reaction at D is RD. So we will take the moment about C is equal to 0. Okay, why moment about C is equal to 0? Because at C we have a internal hinge. Okay, at C we have internal hinge. So this is our internal hinge IH. Okay, so we will take the moment about C is equal to 0 for this portion CD, for the portion CD. So it will be RD times 12. Okay, RD is acting in the anti-clockwise direction about C, so it will be minus negative 12 RD plus 48. What is 48? Is this clockwise concentrated moment at D. So it will be equal to 0 because there is no other moment. So from here you will get the value of RD as 4 kilonewton. Now we have got the value of RD. Okay, so we should find the other values. So at C we have an internal hinge. Okay, so the important thing, or you can say the easiest way to find out all other support reaction, is that we break this beam at C. Okay, as I am drawing here. So here this is our pin support, and this is our moment 48 kilonewton meter. This is our C point C. There will be reaction of 4 kilonewton, which is RD, and here we have our point load of 25 kilonewton at B. This length is 10 meters, this length is also 10 meters, and this length is 12 meter. Now we will consider these two portions separately. Okay, so here we have reaction at D, so it means that there should be a reaction at this point C. Okay, like this will be our reaction. Okay, so both of these reaction will be in opposite direction like this. So first of all, we will consider the this CD portion. Okay, so let me write here for CD, sigma Fy is equal to 0. So from here we will get the value of, sorry, this is not RD, this is RC. Okay, and this is point C. So from here, from this equation you will get the value of RC. Okay, so uh, I will write RC. So for that, for this segment CD, RC is acting downward. Okay, as we have assumed. So minus RC plus 4 kilonewton, which is this reaction at D, plus 4 is equal to 0, because there is no vertical force so other than these two forces in the portion CD. So from here we will get the value of RC as 4 kilonewton. Okay, now we have got the value of RC, so we can find out the value of reaction at A, because this RC, which is acting downward, is equal to RC acting at this point C in the upward direction. This is why we can use this value of RC which we have got from the portion CD for the portion AC. Okay, so this value, the value of RC is 4, and we can find out the reaction RA by applying this equation for portion AC. Sigma Fy is equal to 0, upward direction as positive, and it will be RA, which is acting upward, so it will be taken as positive, minus 25, which is acting downward, plus RC. Okay, RC for this portion AC, it will be acting upward. Okay, so it will be 0. The value of RA is unknown. The value of RC is 4 kilonewton. 4 is equal to 0. So from here we will get the value of RA as 21. Sorry, it will be positive. We will get the value of RA as 21 kilonewton. So we have got the support reactions. Now we can find out the bending moment at different points in the beam. So bending moment at D will be minus 48 kilonewton meter. Bending moment at C will be 0. Okay, because at C we have internal hinge. Bending moment at point B will be equal to plus RC into 10, and the value of RC is 4, so it will be 40 kilonewton meter. Bending moment at A will be 20 RC minus 250 into 10. Okay, and RC is 4, so it will be 80 minus 250. So the value of MA will be minus 170 kilonewton meter. Okay, now we have got the bending moment values at different points, so we can draw the bending moment diagram for the given beam. So this is our reference line, this is A, this is B, this is C. Okay, and at A we have minus 170 and at B we have 40. So this line will go like this. Okay, so this is 170 and 170, this is 40 kilonewton meter. Okay, and at C we have 0 bending moment, and at D we have minus 48 kilonewton meter. So this is like this line will pass through C, and this is our 48 kilonewton meter. 48 kilonewton meter, 40 kilonewton meter, and 170 kilonewton meter. And this is our values of bending moment diagram. So this is negative, this is positive, and this is also negative. A, B, C, and D. So this is our M diagram. M diagram means bending moment diagram. But we need M by EI diagram to apply the loading on this conjugate beam, as there is no change in the section of the beam, which means that the value of EI is constant. Value of EI is constant. We are considering the value of EI as constant for the given problem. Okay, EI means flexural rigidity of the beam. So this M by M diagram can be converted to M by EI diagram by dividing the M diagram with this EI, okay, for each segment of the beam. As there is no change in the EI of the different segment of the beam for segment AC and for segment CD, so this M diagram will remain same as our M by EI diagram, okay. So we will just erase these 4 kilonewton per 4 kilonewton meter, and we will just write 40 by EI, and here we will have 170 by EI, and here and this ordinate we will have 48 by EI, okay. So we know that the length of this portion BC is 10 meter, the length of this portion CD is 12 meter. We know that the length of this portion AB is 10 meter, but we don't know the length of this portion. I should write it as AE, okay. We don't know this point E where the bending moment is 0. So we can find out this AE length. Let us consider that this length EB is x meter, okay. So this length AE will be 10 minus x meter, okay. Now we can use the property of similar triangle, okay. So from similar triangle we will have this ordinate 170, okay, divided by EI, and it will be divided by 10 minus x, and on the other side we will have this ordinate 40 by EI, 40 by EI divided by the x square, okay. This is x. So from here we will get 10 minus x divided by x, 170 by 40, and after solving this equation we will get the value of x as 1.905 meters, okay. Now we know all information about this M by EI diagram, so we can apply this M by EI diagram on the conjugate beam as our loading, okay, on this conjugate beam as our loading. But one important thing which is to be noted here, what will be the direction of the loading on the conjugate beam. So first I have drawn the conjugate beam here, and I will apply the M by EI diagram as loading. So it is 170, it is 40, so it will be like this, and at C we will have 0, and at this point D we have 48 divided by EI. Here we have 40 divided by EI, okay, sorry, 40 divided by EI, and here we have 170 divided by EI, okay. And in our previous first video of this lecture we have learned that if the bending moment is positive, then that bending moment will be applied as upward acting load. So this will be as upward acting load, and if the bending moment is negative, then this bending moment will be applied as downward acting load on the conjugate beam, okay. As you can see here, I am drawing the arrow in the downward direction for this segment also. So this length as the value of x is 1.905, so it will be 10 minus 10 minus x, okay. So it will come out to be, so this length it will be 8.095 meters, and we have called this point as E, okay. We have called this point as E. So this is our B. So this total length E to C, total length from E to C will be 11.905 meter, and we know the length of BC, which is 10 meters, okay, and the length of the segment CD is 12 meters, okay, which is clear. So this is our final conjugate beam, okay. And in the question we have been asked to find out the slope and deflection at internal hinge, and we know that to find out the slope at any point in the real beam we have to find out the shear force in the conjugate beam at that point, and we have to find out the bending moment for finding out the deflection at any point in the real beam. Now to find out shear force and bending moment in conjugate beam at any point, we should know the support reactions at C and D. So let us assume that the reaction at D is R D dash, and the reaction at C is the reaction at C is RC. Let me tell this from here, okay, RC dash. Now we will take the summation of moments about d is equal to 0. Okay, we will take clockwise direction as positive. So first of all, we will have moment due to this triangular loading in the portion AE. So the moment will be minus 1 by 2 170 divided by EI into the base 8.095 meters. Okay, and the distance of this triangular loading of the CG of this triangular loading from the point D. So this is 12 meters. So 12 plus this length is 11.905 plus. Okay, so the CG of this triangular loading will be somewhere here. So it will be 2 by 3 times 8.095 meters. Okay, so this is the bending moment due to this triangle. Now we have another triangle which is in this portion EC. Okay, so the moment will be positive because it is acting in the clockwise direction, and we have considered the clockwise direction as positive. So it will be 1 by 2 times 40 divided by EI multiplied by 11.905 multiplied by distance of CE. So it will be 12 plus 10 plus 11.905 by 3. So this is the bending moment due to this triangle loading on the portion EC. Now we have another triangle which is in this portion CD. So the bending moment due to this triangle will be negative, and I will write here minus 1 by 2 times the length of CD, which is 12 meters, multiplied by 48 divided by EI. It is 48. Sorry, it is 48 multiplied by the distance of CG. So it will be 12 by 3. And another reaction which we have is this RC dash. So the moment due to this RC dash will be 12 RC dash is equal to 0. Okay, so we have got all the moments. So first due to this triangle, the other due to this triangle, and the other due to this third triangle. Okay, and we have also got the moment due to this reaction RC dash. So after solving this equation, you will get the value of this RC dash as 1393.168 divided by EI. Now we have got the value of this RC dash, so we can use the summation of forces in y direction is equal to 0 to find out the other reaction, which is R D dash. Okay, so we will use this equation, and first we have this triangle which is the loading is acting downward. Okay, so the load will be acting downward, which will be taken as negative. So it will be minus 1 by 2 times 170 divided by EI into the length of the segment 8.095. The loading on in the middle portion in this portion EC is acting upward, so it will be taken as positive. So it will be 1 by 2 times 11.905 into 11.905 into 40 divided by EI. Okay, and for the last triangle it will be 1 by 2 times 12 into 48 divided by EI bracket close plus RC dash plus plus RC dash plus RD dash is equal to 0, and we know the value of RC dash which we have got here. So after putting the value of RC dash and solving, you will get the value of RC dash RD dash as minus 655.193 divided by EI. So this is our value of RT dash. Now we have got the reactions. Okay, and we have assumed that the value of reaction at RT is acting upward, but we have got a negative value here, which means that the reaction at T is acting downward. Okay, now let us come to the point. We have to find out the slope and deflection at C, but at C we have an internal hinge. Okay, and one important thing about internal hinge is that, let me draw the deflected shape of the real beam. Okay, so this is our internal hinge. So at internal hinge, when the internal hinge deflects, so it will deflect something like this. As you can see that there is a discontinuity in this deflected shape. Okay, so this deflected shape is also called as elastic curve. Okay, so which means that there will be two slopes at this internal hinge. So first will be this and the other slope will be here. So we will call this slope as theta c left, we will call this slope as theta c right, and we know that this will be our deflection, we will call as delta c. So to find out the shear slope at c, or you can say theta cl, we will write theta cl will be equal to shear force just left of c in conjugate beam. Okay, so the shear force just left of c in conjugate beam will be due to these two triangles. First this AE and the other one is due to this triangle on segment EC. Okay, so I will just write here. So it will be equal to minus 1 by 2 times the ordinate of the first triangle, which is 170, divided by EI multiply the by the distance 8.095, plus 1 by 2 times multiply by 140 by EI into 11.905. So after solving you will get the value of theta CL as minus 449.975 divided by EI. Okay, and according to our sign convention you can also write it as 449.975 divided by EI, and the slope is in clockwise direction. Okay, so we have got the slope just left of internal hinge C. Now we will find out the slope just right of internal hinge at C. So it will be equal to shear force just right of C in our conjugate beam. Okay, now when we were considering the shear force just left of C, we have only two loadings. First due to this triangle AE, and the other one due to this triangle which is acting on the segment EB. Now we are considering the portion just right of C. Now we will have three types of loading. First due to this triangle, the other one due to this triangle, and the other load will be due to this reaction RC dash. Okay, so I will write here the first loading will be due to the first triangle 1 by 2 times 170 by EI multiply by 8.095, plus the load due to the second triangle 1 by 2 40 divided by EI multiply by 11.905, and the third one will be due to the reaction RC dash. And we know the value of RC dash. After putting the value of RC dash in this equation, we will get the value of theta c right as 943.193 divided by EI. Okay, we are getting a positive value of the theta cr, which means that this theta c is like this. Okay, the theta c is like this. Positive value means the slope is anti-clockwise. Okay, so this is the direction of the slope just right of internal hinge C. We have got the slope at internal hinge. Now we are going to find out the deflection at internal hinge. So the deflection at internal hinge in real beam will be equal to bending moment at C in the conjugate beam. Okay, so the bending moment at C in the conjugate beam we can find out from by considering the forces on the segment CD, or by considering the forces on the segment AC. So the easiest way is to consider the bending moment at C by considering the portion CD. Okay, so when we are considering the portion CD, so the moment due to this triangle loading acting on portion CD, and the other moment will be due to this reaction RD dash. Okay, so I will just write directly the bending moment. So first I will write the bending moment uh, due to the triangular loading which is acting downward, so it will be taken as negative. So it will be 1 by 2 times 12. The 12 is the length of the triangle, or you can say base of the triangle. 48 divided by EI multiply by 2 by 3 into 12. So 2 by 3 is the distance of CG of that triangle from point C, and we will have 12 R d dash. Okay, and we know the value of rd dash, which is I will just write this first, so you can calculate this value. So after calculation you will get 2304 divided by ei minus, okay, the value of rd dash is negative, so I have put a negative sign here, and the value of rd dash is 655.193 divided by ei, and after solving, or you can say after calculation, you will get the value of delta c as minus 101 minus 10166.316 divided by ei. Okay, and this is negative, which means that our deflection is delta c is downward. Okay, so this is it for this video, and we will meet in our next video. Thanks for watching.